Hey, Zach, thank you. It's a pleasure to be here. As Zach said, we've been doing a lot of work, individual groups, over the last year and a half since the field campaign. Some of those amongst the groups are starting to become synthesized. Some are still sort of need to be synthesized. So you'll probably hear some, we're in the midst of the analysis. We've probably have some divergent opinions on where things are going, but that's where the state of the discussion is at this point. So I'm going to start out with kind of a broad overview. I know you've already heard quite a bit about the field campaign, and then I'll go into some of the work that we've been focusing on, and then Charlie will broaden that out and specifically talk about the work that's been done at the Zion Supersite. So the campaign was May and June of 2017. This is a schematic from NASA that illustrates all the different assets and also the different participants. I've listed each one of the primary co-authors on the synthesis report. And so this is a big effort. I'm just summarizing the work of a large number of people. So hopefully, can you see my slides? Did it progress for everybody?
Yep, looks great.
Okay, so brief overview of the overall objectives. What were we trying to do during LMOS 2017? Basically, we're trying to provide observations so that we can improve the air quality modeling that's necessary to do for state implementation planning. That's the fundamental reason we're doing this. So a lot of the post-mission analysis is using these measurements to try and improve our ability to model the unique meteorology and chemistry along Lake Michigan. In particular, focusing on trying to get a better understanding of lakes or ozone gradients and why they occur. Again, I said there's a number of different institutions that were involved in LMOS. We had major federal contributions from NOAA, NASA, US EPA. There was a number of different universities that were participating: University of Wisconsin, University of Iowa, Minnesota, Northern Iowa, Maryland, Baltimore County. A lot of that was under an NSF proposal that Charlie led. And then we had scientific aviation that was providing additional measurements supported by the Electric Power Research Institute. In addition to those federal and universities, we had a number of air quality management agencies kind of under the consortium of LADCO that were directly involved in the campaign, in particular Wisconsin DNR, Illinois EPA, and Indiana DEM that provided both measurements and ground sites to support the campaign. So this is a slide from Donna Kinsky at LADCO. This is an updated set of 2018 ozone design values. And we can see that, again, much of the exceedances, these are now colored by the new NAC standard. Greater than 70 parts per billion of ozone are in orange or red. And you can see that we have localized areas in some of the urban centers, but we have our largest issue along particularly the western shore of Lake Michigan. So highest 8 sites are all around Lake Michigan, and a significant number of sites are over 75 parts per billion. So that's the environment that we're working in, and our objective is to try and understand the reasons for those coastal exceedances. Again, the foundation for this is fairly well understood. Lake Michigan and the association between lake breezes and ozone enhancements have been studied for a long time. Just as a refresher, during the evening, the land breeze blows ozone and precursors offshore out over the lake, where you can get a convergence zone in a fairly shallow marine boundary layer. And then during the daytime, these ozone and ozone precursors that have been sitting over the lake in a shallow marine boundary layer are advected back onshore, and we develop another convergence zone if the prevailing winds are correct, and can lead to significant enhancements in ozone precursors and ozone production. So that's the understanding, and a lot of what we're trying to do during the Lake Michigan Ozone Study is collect measurements, both chemical and meteorological measurements, to really quantify that canonical view and then use it to help improve our ability to model this very unique environment. So this is a picture from the new VIIRS sensor on the operational NOAA satellites, follow on to MODIS. This is on June 9th, 2017, during the field campaign. And you can see from the cloud field that there's this convergence zone on the western shore of Lake Michigan because we've got prevailing westerly winds and that lake breeze is impacting those winds. If we kind of highlight where that lake breeze front is, again, you can see that on the western side of the lake, we've got this convergence zone, and as a result of that, you get kind of more fair weather cumulus popping up on the eastern side of the lake because, again, the winds are prevailing to the northwest. From the northwest, you can see that the lake breeze actually penetrates much deeper because it's with the wind and less of a convergence zone. I'm not going to go through this slide in detail, but this is a summary of the various measurements that were made during the field campaign. We had two major super sites, one at Spaceport Sheboygan within the town of Sheboygan, Wisconsin. This had both EPA in situ measurements and then remote sensing measurements, and then a second super site at Zion, Illinois, which had remote sensing measurements from the University of Northern Iowa, and then very detailed in situ chemical measurements. And I'm going to leave that discussion to Charlie's part of the talk. We also had a number of different airborne platforms, including a remote sensing instrument called Geotasso that was from NASA. This allows us to do mapping of abundances of nitrogen dioxide, and also an in situ airborne measurement suite from Scientific Aviation that allows us to do profiling. And I'm going to focus a lot on those measurements. We had ship-based platforms, and Charlie will talk briefly about some of those too. I don't believe we're going to have much time to talk about the mobile platform during this particular presentation. So I came into this from a NOAA perspective, and one of my objectives was to evaluate the current operational air quality forecast that the National Weather Service puts out. This is the NAM-CMAQ model. And of particular interest was work from Patricia Cleary, who was also part of this campaign, who looked at ferry transects across Lake Michigan and compared the ozone measured from those ferry transects with forecasts from the National Weather Service operational air quality forecast. And this figure here shows the results from between 2008 to 2010. And what it's showing is that during this time period, the operational model had a fairly significant positive bias in predicting ozone over the Great Lakes region. All these colors are positive biases. Over the lake, you can see that biases are between 14 and 16 parts per billion. This is at 20 UTC, which is in the evening. And so this is kind of where the community sense of how the models would tend to behave were. But this is based on a model during the 2008 to 2010 time period. This is a slide now. So this is a pollution rose slide. On the left-hand slide is showing the observations at the Sheboygan Kohler-Andre site. On the right-hand side shows the NAM-CMAQ National Weather Service forecast during the LMOS 2017 campaign. So the length of the wind rose is an indication of the percentage of time the wind was from that prediction, and the colors are an indication of the different fractions of ozone that were observed or predicted under different ozone levels. So ozone mixing ratios above 60 parts per billion and above 80 parts per billion are in yellow and red. And what you can see is that at Sheboygan Kohler-Andre, when we have winds, prevailing winds from the south-southwest, we see ozone enhancements above 60 parts per billion or above 80 parts per billion about 11% of the time during the field campaign. That's not just during the ozone exceedance periods, but it's during the whole campaign. Whereas the NAM-CMAQ model only shows ozone enhancements above 60 parts per billion 1% of the time during the field campaign. Most of it is observed at very low levels, above 20, but less than 40. And so we can see that during the LMOS 2017 campaign, there was a very significant underestimate in ozone at Col Andre, very different than the kind of canonical view that the community had from previous modeling studies. You can also see for this National Weather Service forecast that it's not capturing the prevailing southwesterly winds at Col Andre site. So this is a summary of the airborne measurements that were collected during the field campaign. On the left-hand side are all the flight tracks for our remote sensing platform. So this is an airborne sensor that looks down and measures reflected radiation, and from that it can retrieve the amount of NO2 below the plane. It's colored by the different flight days during the field campaign. And what you can see by the patterns, we're doing raster patterns. We're basically doing mapping so that we do a transect and then turn around and do a transect that intersects the previous one. And we've got transects that are designed to look at what's going on in the Chicago emissions region to the south, what's going along the shoreline between Chicago and Sheboygan, these north-south transects, and then various east-west transects that are trying to look at what cross-sections of some of these column abundances are. Associated with each one of those flight plans, we also deployed the scientific aviation aircraft, and it was doing in situ spiraling. So each one of these points where you see large circles is where we've got a waypoint that we're doing spirals so that we can get an idea of what the vertical distribution of ozone, NO2, temperature, and water vapor are associated with the column measurements we're observing from the remote sensing instrument. So again, we had a number of different flights. The synthesis report goes through the meteorology during the period, and I'm not going to go into detail on that, but the early part of the period was fairly cool, prevailing westerly or northwesterly winds. It wasn't until in June that we started getting significant ozone events. As an example of how you can combine these two measurement platforms, this is an example on Sunday, June 18th and Monday, June 19th, morning flights from 8 till 10 local daylight time. And here we're using both of these instruments to get an assessment of what the weekday-weekend effect is in terms of NO2 emissions. So on Sunday, the column amounts that we get from the Geotasso instrument are low. This is shown in differential slant column, but you can think of it as the overall column abundance. On Monday, again with prevailing westerly winds, so similar meteorological conditions, you can see that there's been significant enhancements in the emissions. And we can look at the outflow from Chicago with some of the aircraft spirals, which are shown in the offshore, and then their vertical profile down in the the boxes on the left and right-hand side. And you can see that the in situ NO2 was below 2 parts per billion on Sunday offshore from Chicago, and up to 12 parts per billion during both of those profiles on Monday. So we're in the scientific aviation data is finalized. It's available on the NASA archive. Intermediate retrievals from the Geotasso instrument, which give us column abundances, are also on the archive. And right now, Laura Judd at NASA Langley is finalizing those retrievals so that we actually get a true tropospheric column abundance instead of this slant column. And once we have those, then we're able to do very quantitative comparisons between these Geotasso column measurements and predictions from the models. So what I'm going to focus on now is looking at a particular ozone event that occurred on June 2nd. This is a slide from Angie Dickens from the Wisconsin DNR. On the right-hand side shows the MD A8 ozone on June 2nd, and again, you can see that the exceedances are restricted to a very narrow zone along the coast. June 2nd, we've got time series at both the Kohler Andre site and then the Sheboygan Haven site, which is slightly inland. And you can see on June 2nd, the enhancement at Kohler Andre was quite a bit higher than the Haven site. And then we've got time series at Chewauquee and the Chewauquee, Kenosha Water Tower, and Zion on the bottom. And there you can see that at the Zion site, which is the southern super site, we have very consistent peak ozone. So this was one of our kind of golden days where we had a kind of a classic lake breeze circulation and significant ozone enhancements. So one of the suite of instruments that we deployed was ground-based instruments that also were able to measure column NO2 abundances. Unlike the aircraft, which would fly on a given day and do mapping, these were deployed throughout the field campaign and gave us continued measurements at various different sites. So starting in the south, we had one at Schiller Park in Chicago, just north of O'Hare Airport. We had an instrument at Zion, one at Milwaukee, one at Grafton, and one at Sheboygan. The figures that are shown here are diurnal averages for all the different days. The solid black line is the weekday, and the dashed black line is the weekend. And so you can see at Schiller Park this same kind of enhancement that we saw on a particular weekday weekend is occurring throughout the field campaign. And then in red is this June 2nd period when we saw these very high ozone enhancements along the lakeshore. And you can see at Schiller Park, June 2nd was one of the days that was the highest diurnal variation in column NO2 at Schiller Park. You can see enhancements that are the largest observed during the campaign at Zion that occur about 12 p.m. And then as you move up the shore, Grafton shows slight enhancements. Milwaukee, we didn't have data for June 2nd. And Sheboygan, we see a much later in the evening enhancement on June 2nd. And so this suggests transport along the shore and up towards Spaceport Sheboygan, where it was observed later on the day. But that's not necessarily true. We need to look more carefully at what the contributions from local emissions are, as well as transport along the shore. So, going to continue focusing on this coastal ozone exceedance day, June 2nd. These are now figures that show the in situ aircraft measurements on June 2nd. I'm going to slow down a little bit so people get used to seeing these figures. So we're looking at a three-dimensional distribution of where the aircraft went. The aircraft starts out in Sheboygan County Airport, and it takes off and it heads towards Spaceport Sheboygan, where it does a vertical spiral. Then it does an offshore spiral, and then it comes down and it goes through to a spiral over offshore from Milwaukee down to Zion, where it does another spiral over the Zion supersite, an offshore supersite, and then it comes back to Sheboygan. The distribution of ozone that was observed. This is the distribution of NO2 on a log scale. This is the distribution of relative humidity, and this is the distribution of temperature. What I'd like you to focus on are the very subtle enhancements in ozone offshore Sheboygan and offshore Milwaukee, NO2 offshore Sheboygan and offshore Milwaukee in this very, very shallow marine boundary layer. And we know that because we can see that the aircraft just dipped into this region, which is colder than the air aloft and more moist in terms of relative humidity. So it's these very, very shallow features over the lake, and these are less than 200 meters thick, where we're seeing the majority of the photochemistry going on, and that kind of just indicates the degree of accuracy we have to be able to be modeling these kind of processes if we're going to capture the photochemistry that's going on. In these aircraft observations, we're always spiraling up to 3 kilometers so that we can make sure that we get out of that return layer, terrestrial boundary layer, as it's out over the lake. And so a lot of this information up here is information that's going to be air masses that are going to be potentially mixed down into this marine boundary layer, and we have very good sampling of that throughout the campaign as well. So now, again, I'm going to look at how well did the National Weather Service NAM-CMAQ model perform on this particular day. Again, this is the same ozone observations that we saw on the previous slide with very significant enhancements. Ozone above 110 parts per billion offshore Milwaukee throughout extensive region, up above 80 to 90 parts per billion offshore of Sheboygan. And here's the NAM-CMAQ prediction. We don't have any predictions above 80 parts per billion anywhere out over the lake. And we also see that there's a very significant underestimate in ozone in this return layer associated with the terrestrial boundary layer that's out over the marine boundary layer. This is a summary now in the same wind rose plot that we showed before, except now it's a pollution rose for these observations along the aircraft. And what you can see is that in the marine boundary layer, this is the lower level southeasterly flow over the lake in this way. That's where we had the observed ozone enhancements with 51% of the observations above 75 parts per billion and even 3% above 100 parts per billion. This is significantly underestimated in the model. This is the westerlies that are aloft, so this is in this return flow layer here. And again, you can see that the model is significantly underestimating ozone in that region. So we began exploring what the role of biogenic VOCs were in contributing to the model underestimate in ozone out over the lake. So the isoprene and biogenic VOC emissions increase during leaf out. The LMOS period in May and June is a period where we have very rapid change in the leaf out, the greening of the Midwest region. So this shows leaf area index, which is just a measure of the leaf out based on satellite measurements. On May 1st, you can see leaf out has occurred here, but it still has not occurred over the Midwest. And as we go to June 2nd, you can see this very dramatic change in leaf out, and even leaf out along the shore of Lake Michigan that might be ahead of other regions in southern Wisconsin. And then by July 4th, you can see that now we've leafed out everywhere. So what air quality models do in terms of estimating biogenic emissions is they typically use climatological distributions of leaf area index to predict that leaf out. If a particular season evolves sooner or delayed compared to climatology, you'll have very different changes in how these biogenic emissions, the timing of them, and this can feed back on ozone production, particularly ozone production downstream from urban areas with enhanced VOCs. So we conducted with NAM-CMAQ, with the National Weather Service model, sensitivity experiments where we simply doubled the biogenic VOCs. These are measurements by the EPA at the EPA trailer in Sheboygan, Wisconsin. The black line is the observed formaldehyde. The red line is the control, the operational NAM-CMAQ prediction. And you can see we've got a low bias in formaldehyde, one of the byproducts of biogenic emissions. When we double the biogenic emissions, you can see that we get a fairly significant increase and much better agreement with the observations at Sheboygan. So the overall bias goes down quite significantly so that we're left with a very small positive bias. What's the impact on ozone? Within the National Weather Service forecast model, the top figure shows the control experiment again on June 2nd, where we know we were significantly underestimating ozone, both along the shore and out over the lake. The bottom figure shows surface ozone from NAM-CMAQ with the 2 times the biogenic emissions. And you can see that we've filled in this gap in ozone enhancement in the middle of the lake, and are now in much better agreement with the monitoring sites along the coast. So within NAM-CMAQ, we get about a 30 part per billion increase in surface ozone by doubling biogenic emissions. And Charlie's going to follow up when he talks with details using other chemical mechanisms and other modeling platforms. So the last part of my talk, I'm going to talk about some of the work we're doing now post-mission. This is work that's funded by the NASA Health and Air Quality Applied Science Program, and we're partnering with LADCO and the Wisconsin DNR to do regulatory model development so we can improve the meteorological platform that's being used for the SIP modeling in the region. So what we've been doing over the last year is doing WRF simulations, testing both various physical parameterizations and also different resolutions. The domain that's shown here shows our overall 12-kilometer domain, which is the continental U.S., a 4-kilometer domain indicated by D2, which is the LADCO region, and then a 1.3-kilometer WRF domain that focuses on the Lake Michigan region. And we've been conducting experiments looking at fundamentally 2 different physical configurations. One that we're referring to as the EPA baseline. It's using the asymmetric convection model version 2, and it's applying to land surface scheme. And then a second physics package, combination that we're using, which is using the YSU PBL scheme, excuse me, the NOAA land surface model, and a different parameterization for our clouds. Excuse me. So I'm going to show very quickly the results of some of these experiments. Here we're looking at normalized mean air for temperatures in degrees Celsius versus normalized mean bias. Ideally, we would want to have all the results down here. These are for all the different, these are for the coastal monitoring sites the Wisconsin DNR has in operation. So Sheboygan, Colorado, Haven, Newport, Milwaukee, Manitowoc, Lake Geneva, and Chewauquee. Consider Lake Geneva as kind of an inland site that would be less influenced by the lake breeze processes. These are results for the 12-kilometer domain, and we've got the squares, triangles, and diamonds are our YNT configuration, and the crosses and stars are the EPA baseline configuration. What you can see, interestingly enough, is Sheboygan Haven behaves very much like Lake Geneva in terms of an inland site and has the best overall statistics, low biases, lower normalized mean airs of any of the sites. Whereas if we look at Sheboygan and Chewauquee, they have the worst statistics in all cases at Sheboygan in terms of normalized mean air and biases, and generally has the worst statistics at Chewauquee, although we do see at 12 kilometers the EPA baseline configuration actually performs pretty good at Chewauquee. That's 12 kilometers. If we go down to 4 kilometers, we can see, I'll toggle back and forth, you can see that the differences at Sheboygan Haven or Lake Geneva has changed very little, but we've had a significant reduction in both the biases and the airs at Sheboygan, Colorado, and at Chewauquee for all the configurations. And now if we go down to 1.3 kilometers, what we see is that for the YNT configurations, we continue to get reductions in the mean, normalized mean air and mean bias. So that's these two boxes. But for the EPA baseline configuration, at least strongly at Col-Andre, we actually get a degradation in the normalized mean air. So we go from here at 4 kilometers up to here. So we're seeing some difference in the behavior of these different physical schemes when we go to higher resolution, and we're in the process of exploring that further. So one of the ways that we're exploring that further is now to take advantage of some of the remote sensing observations that were conducted at Spaceport Sheboygan. This is boundary layer profiling that we're doing with an instrument called ARI, which is an upward-looking infrared instrument, a Doppler wind LiDAR, and an aerosol LiDAR that I won't be talking about today. And what these measurements do is allow us to start now looking at the diurnal behavior of the boundary layer right along the shore throughout the mission. And in particular, we're looking at this nighttime stable layer over the land, the development of the mixed layer in the morning, and not shown on here is the penetration of the lake breeze circulation. So, and then this residual layer that we were discussing with some of the aircraft measurements. So I'll let this sit up for a while too, because this is a busy slide. On the left-hand side, we have the retrieved temperature profile in altitude above the ground versus time in GMT. So this is the morning, this is sunrise, this is nighttime, and this is during the daytime. So this is temperatures, this is wind direction, and then this is wind speed. Those are the observations. This is the prediction from the 12-kilometer EPA baseline. The lake breeze you can see here as this period that interrupts the daytime growth of the convective boundary layer, and you have this penetration of the colder air from the marine boundary layer in over this site. At the same time, you have this very dramatic shift from northwesterly winds to southeasterly winds with this lake breeze coming on shore, and a reduction in the overall wind speed as the lake breeze comes on shore too. This is what the 12-kilometer EPA baseline shows, and you can see that at 12 kilometers, there's no indication of a lake breeze circulation at all. It doesn't capture the distribution of the winds in the lowest kilometer very accurately at all, and it underestimates the overall wind speed, again, in this 400 to 600 meter layer, which would be associated with nocturnal jet activity at the 12-kilometer for the EPA baseline. If we look at the 12-kilometer for our YSU configuration, except for differences in the nighttime stable boundary layer, you actually don't see very significant differences in its ability to capture the lake breeze. So neither configuration at 12 kilometers is able to capture the lake breeze. And again, I forgot to mention, this is specifically for June 2nd, this day where we had the significant ozone enhancement. Now I'm going to show results for the 1.3 kilometer resolution runs. This is the EPA baseline. And again, what it appears to me is that you've reduced the nighttime stability in that stable nighttime terrestrial boundary layer, but there's only a hint of a lake breeze circulation coming in, and if it is coming in, the timing of it is significantly different than what was observed. So at 1.3 kilometers, we have a very different solution, but we still have poor performance for the lake breeze circulation within this 1.3 kilometer EPA baseline. If we go to the 1.3 kilometer, and I should not have that 12 kilometer there, sorry, YSU configuration, now we can see that we are starting to capture a lake breeze circulation. We're capturing this morning time convective boundary layer growth that's observed. And in particular, we're capturing the timing and the vertical extent of the switch in wind direction associated with the onset of that lake breeze. However, we're still underestimating the strength of this nocturnal enhancement in winds that we see at Sheboygan. And again, this is critical because this is transport within the lowest layers out over the lake, and it could have a very big impact on what kind of precursor emissions are above the marine boundary layer. So to summarize part one, we find that during the Lake Michigan Ozone Study in 2017, the operational National Weather Service model underestimates coastal ozone, unlike previous studies. This is largely due to changes in emissions that the model's using between 2008, 2010, and 2017. Lake Michigan ozone production during LMOS 2017 appears to be very sensitive to VOCs, biogenic VOCs, and their interaction with a high NOx urban plume within the stable marine boundary layer. WRF modeling studies show that neither the EPA baseline or the Y&T platforms are able to capture the lake breeze at 12-kilometer resolution, and that the Y&T platform is better at capturing the lake breeze circulations when we go to higher resolution experiments. And with that, I'm going to pass it on to Charlie. So I should stop sharing my screen, right?
Sure, yeah, thanks, Brad. If anybody has any questions for Brad, as I mentioned, you can go to the webinar client and raise your hand by clicking the box next to your name in the column with the hand on it, or you could type a question into the questions box. And I'm going to pass the presenter rights over to Charlie Stenier now, but if you have any questions, please either raise your hand or type into the questions box. All right. Charlie, you should now have a, there you go. All right, we see your screen.
So do you see presenter view, or does it look okay?
It's in presenter mode.
Okay. How about now?
It's in full screen mode now.
Okay. All right.
Your audience view, I think, is your webinar pane is covering the slides.
Oh yeah, click that little, there you go. It's gone.
All right. I want to acknowledge lots of co-authors, and in developing this presentation, I had a choice to make. One option was to stick to the older results that are more fully developed and that are in the synthesis report that we put online about 2 weeks ago. And I could have just explained what was in there, but I chose option B, which is to present a lot of fresh results that are not fully represented in the synthesis report. And so this is new material, and Tim Bertram, Michael Bermule, Betsy Stone, Dagan Hughes were kind enough to either present or allow me to present this newer material. So with that is the caveat that some of this might change. We're just getting into these inner comparisons between groups, and not all the checks on all these conclusions and data points have been done.
And Charlie, let me mention that Michael and Betsy and some others from the LMOS team are on the webinar. If you'd like me to unmute them so that they can contribute to this discussion, please let me know.
Not yet, but we'll get there. So here's my favorite picture of the Zion site. There was a continual rainbow over the site for the whole field campaign. But we took these two trailers, filled them with the chemical instrumentation, and then it was surrounded it by the not shown are the integrated samples to pull the filters. You can see, let's see, I think that's a pointer, right? There's the Pandora. I'm sorry, the salometer. The Pandora is here, continually looking at the sun to get that NO2 profile. The Zion site, the satellite view is right here. So it was 1 kilometer from the lake, and it was in a state park. And then it was about 4 kilometers from the Chewauke Prairie location, which had the nearest PM 2.5 measurement. So we had ozone and NO2 and all our campaign-specific measurements here, and then we had a long-term regulatory site here with PM and ozone. Local sources, Metro Rail was about 600 meters to the west of the site, and then the main road for traffic north-south in Zion was about 1.3 kilometers to the west. So this is a list of everything that was measured at Zion, and data from all of these instruments is in the repository, which is public. So you can go download data in standardized file formats for all of these, contact the PIs, and we're just discussing a small subset of this today. The lake breeze was apparent at Zion, and we could feel it on site, and you can see it in the windrows. So these pieces to the southeast were representing the lake breeze at Zion. If we look at conditional probability functions, so this is showing for a bunch of different wind directions, the fraction that NOx was elevated. I think this was probably over 15 parts per billion. So when the lake breeze came in, 10% of the samples had NOx over 10 parts per billion, and that was very uncommon for other wind directions. And then over on the right is the conditional probability function for ozone, and these are concentrations above 70 parts per billion. So I'm going to briefly introduce the different modeling systems that I'll be using in the presentation. One is the WRF-Chem modeling system from the University of Iowa. I know this is a busy slide, but this is our post-analysis. So we had a forecast model, which I'm not going to discuss today. This was our post-analysis configuration. So 4-kilometer resolution, and our emissions are NEI 2011 with a 28% reduction in anthropogenic NOx. And then I'm just going to touch on things that may be important. Our chemical mechanism is down here towards the bottom. It's the Rackham chemistry with an ESRL update. And so the red asterisks indicate areas where we've done sensitivity studies. So this is a fairly standard photochemical grid model. The key difference between this and the NAM-CMAC that Brad was discussing is we have full feedbacks between meteorology and air quality. So if there are aerosols that develop that change the radiation, that changes the energy budget at the surface, and that will change the temperature, which will change the biogenic emissions, and so on and so forth. Here's just a schematic showing those 4-kilometer grid cells, and luck will have it that the way the 4-kilometer grid cells fell over the Zion site, that the Zion site was in a grid that's represented as about 40% land and about 60% lake. We're also going to show results from the Wisconsin Master Chemical Mechanism Trajectory Model. And so I just give, this is a quite different type of model. So this is a 0D model, so it's a box model. And I'm showing the trajectory for June 2nd, starting in Chicago, traveling out over the lake in the morning, and then coming back on shore at the Zion site. So this is a back trajectory from the peak ozone period at Zion for June 2nd. So the Bertram group implemented the master chemical mechanism here, which had 8,401 reactions. So as many more reactions than you would put in the 3D model. But since you're only solving for one grid cell, it's much more computationally tractable to have so many reactions. And then wherever possible, you use measured values to constrain the model. And then what the Bertram group did was have the appropriate NEI emissions enter into the box at each time as it traveled through the domain, as well as the similar Megan biogenic emissions that we would use in a 3D model. Michael, is there anything, this would be a good time to unmute Michael. Is there anything you want to add about the method that you think is important?
Hear me?
Yeah.
No, I don't. I think you went over it generally. I think when you go to the further slides, I could elaborate more on that if you want. But it's just a pretty basic backward trajectory model with grids that you just put in all your missions for, solve for.
Thanks. So now I'm going to switch presentations and have Dagan Hughes present. I just have to figure out how to change. How's that look? Do people see a title slide?
Looks good. Yeah, looks good.
You're talking into the hockey puck phone.
Okay. So I'm Dagan Hughes. I work for Dr. Betsy Stone here at the University of Iowa. And so I was just going to give some updates on some of the organic tracer analysis that we've done with our aerosol samples. Our main goal is to investigate the distribution between primary and secondary and anthropogenic and biogenic sources of PM2.5 and Zion. So in total across the study period, PM2.5 was largely composed of organic matter with smaller contributions from inorganic ions such as sulfate, ammonium, and nitrate, as well as from elemental carbon. And then on this slide, something that we've kind of changed since the initial synthesis report is breaking up these periods of elevated ozone. So with period A being on June 2nd, period B and C were originally combined together, but now we've separated out period B being June 10th through 12th, and period C being June 13th through 16th. And that was simply based on the data that we've seen from some of the secondary tracers that I will discuss in just a moment. You can. Sorry. Maybe. Okay. So breaking this up into those periods and looking at the average concentrations across, we see a few differences, specifically that PM2.5 mass is elevated along with elevated concentrations of ozone. So on ozone period A or June 2nd, when we had the highest concentration of ozone that we observed, or hourly ozone concentration, we also see the highest PM 2.5 concentrations. And then looking at the differences in OC, organic carbon and elemental carbon between these 4 periods, we see that ozone period A has a very low OC/DC ratio of only 7, which is indicative of greater influence or relative influence from combustion sources. Comparing ozone period B and C, we see that ozone period B has an OC to EC ratio of 17.9, which is suggesting that it's highly influenced by SOA formation. And then compared to C, of an OC/EC ratio of 11.3 is relatively similar to the background or the periods that were not experiencing elevated ozone episodes, which is kind of the reason why we decided to separate these out and then investigate this further by looking at SOA tracers. And so on the next slide is the initial analysis of our SOA tracers. And so we started with organosulfates, which are useful in providing information on how biogenic emissions or biogenic SOA formation is influenced in the presence of sulfate. And so the 3 most abundant organosulfates that we observed were isoprene derived, with 2-methyltetrasulfate being the most abundant. And we see that we have contributions to organic mass across the study period, but in total, these 3 alone account for 3% of organic matter. And then in specific differences between B and C, we see that there's like a 10 times increase in ozone period B relative to the rest of the study. And more interestingly is that during ozone period B, we have the highest concentrations, and these dramatically drop off during ozone period C. And then, so to look at this, we found that they're largely dependent upon isoprene concentration, so that in the beginning of the study, when isoprene emissions were relatively low, we saw relatively low concentrations of these organosulfates. However, again, between period B and C, once we do have that high isoprene available, we do see a greater increase in ozone period B, but we're seeing a lesser increase in ozone period C. So really trying to investigate why there's this dramatic drop in between that is something that I'm currently working on, and looking at differences in meteorology, differences in relative humidity, also looking at aerosol pH calculations to try to better understand and constrain what is driving this dramatic decrease in SOA formation between these 2 periods. And something to look at now is the GCMS analysis that I'm currently working on, and then comparing those to what I'm seeing with the organosulfates. So starting with low NOx tracers as 2-methyltetrals, we see the same trend occurring, where in ozone period B, we're seeing about a 10 times higher concentration, but I'm still in the process of extracting and analyzing these samples, so I don't have a large background to compare to yet. But this generally following the same trend that we're seeing with 2-methyltetrasulfate, in that we have a very high abundance in ozone period B and then a low abundance in ozone period C. And then for the NOx tracers, 2-methylglyceric acid, we do see that they're elevated in ozone period B, but also we do see a daily highs in ozone period C. However, when it comes to SOA formation or methylglyceric acid sulfate, we see that concentration dramatically drop in ozone period C. And so again, this is something that I'm currently working on trying to constrain and understand, and hopefully we'll be able to get that accomplished soon. The other tracer that we were measuring by GCMS is levoglucosan. We saw at this time right now 2 very high samples on June 7th and June 8th. And then I pulled the high time resolution PM 2.5 data to kind of look at this. And as we see it increasing on those 2 days as well, which suggests that it's a local source, not a transport source. So we are seeing influence from local combustion or biomass burning at the site, and then we will continue to look at the other samples to see other days that are influenced by biomass burning. And so just to kind of summarize some of the sources that we've identified thus far based on our initial analysis, we are seeing influence in terms of primaries from biomass burning and windblown dust. I expect to see, or based on previous studies, we expect to see vegetative detritus, but we are still working on getting that data worked up. And then in terms of SOA formation, we are seeing contributions from isoprene and terpenes as well. And then anthropogenic-wise, we've seen diesel and gasoline engine indications from both elemental carbon and hopanes. We've also seen some industry, and we're expecting to see coal burning and ship emissions and additional industrial sources as we get the GCMS SOA tracers analyzed and we include the analysis of metals. So future work is going to involve completing the analysis of primary and molecular markers as well as our SOA tracers from GCMS, and then including a quantification of metals, and then taking this data and implementing it with positive matrix factorization to estimate the sources that are contributing and also estimate their contribution so we can identify the major ones there. So that was.
Thanks, Dagan. All right, so just the high-level overview of the campaign as seen from the Zion and Kohler-Andre ozone monitors. So this is what Dagan was referring to as, I guess I need that pointer again. Period A, and then you said period B was
10th to 13th.
10th through 13th, so here, and then period C here. Looking at now PM 2.5 and ozone at Zion, you see there are some days where there's an anti-correlation, where PM goes up at night, and NOx titration of ozone drops the ozone. So for example, May 26 is a great example of that. But then when we get to these peak ozone days, as Dagan was showing through the integrated samples, we get increases in PM at the same time as we get increases in ozone, because these plumes that are coming on shore have SOA, they have primary aerosols from the source regions, and they have ozone. And you see that here, and then we see it during the 11th, the 12th, again on the 14th. So switching gears to the WRF-Chem modeling results. First I'm going to talk about meteorology. And so big shout out to Miriam Abdi. I'm showing a lot of her work. So she divided the domain into these 5 zones, and I'm going to focus slightly more on zone 1, which is the west coast of Lake Michigan, and these specific monitors. And when we looked at our base model run, we were too cold. So the model's in red. This is the diurnal temperature profile versus the observations. And so you see sort of 3 to 4 degrees too cold in zone 1. And then here's dew points. And so higher dew points or higher water content in the atmosphere. And you see during the afternoon, the model was too moist. Now, being too cold is a problem for ozone modeling, because we get too low on the biogenic emissions are temperature sensitive, and that's a major precursor for ozone, and the kinetics of the reactions are temperature sensitive. So that was something that Miriam was trying to fix, and this is a big list of sensitivity studies. And one thing that I'm going to focus on a little bit is the meteorological initial and boundary conditions. We started with the 1 degree GFS because that was good for forecasting. But then later we tried the high resolution rapid refresh at 3 kilometer, which has a lot more data assimilation. And so it's a little bit busy, but all the red bars are for the base model. All the green bars are for after we've changed to the HER model with the NOAA land surface. And This is now bias. And so I said in zone 1 we were cold. And so that's this negative 2.5 degrees cold during the day in our base model in zone 1, and then negative 2.5 degrees cold during the night in zone 1. And then the additional bars are for the other zones in the domain. And then these are root mean squared errors. And when you square the error, they all become positive. So these are all above 0. And then here is the dew point. So this is water vapor in the atmosphere. And as I said, initially we're too moist, especially during the day. And these first 5 bars are for the day. The second 5 bars are for the night. So when we switch to the HER-NOAA modeling system, you can see everything, it gets better everywhere. And it gets better during day and during night. So this was a pretty positive development for us, because our mean temperature biases go to about 0, which was one of the major goals, especially during daytime. So these are the change in temperature from going from the 1 degree GFS to the HER for our initial and boundary condition for the MET model. And you can see the red are temperature increases. We were too cold. We needed warmer conditions. And you see this broad band of about 2 to 3 degrees warmer. And then you can see some specific features around the lake. For water vapor, the red indicates that this change made us moister, and the blue indicates drier. And so you can see over the water bodies, we became moister with this change to a higher resolution, more data assimilated initial and boundary condition. And then where we were too moist, it dried us out. I found it interesting that over these river valleys, it didn't dry it out as much. So that seemed physically plausible to me. And here's the change in ozone that we got from that. So about a 2 degree air temperature change on average led to about a 3 degree on average increase in ozone. And I've circled places that had the largest ozone increases were here, and they spatially are correlated with the largest temperature increases as well. There's many other comparisons we can do, and because of time, I'm not going to go through them. We also compared to scientific aviation, and that gives similar conclusions. And an additional sensitivity test that we ran was to use very finer lake surface temperatures. And it gives very similar results to switching out the initial and boundary conditions with HER. It's just limited spatially to right around the lake, whereas switching out the initial and boundary conditions with HER applies over the whole domain. One comparison I'll show, which is similar to the ARI stuff that Brad was showing. So these are the SODAR at Zion. And so this is a 24-hour period. The times are in UTC, and green indicates flows from the west, and the white in this case is flow from the south, and then the reds are flow from the east. And so the time when the lake breeze came in was at about 14 UTC. And you can see that the prevailing westerly wind switched to easterly rather abruptly. In our base model, it did have a lake breeze, but it was about 4 hours too late. After making the change to the HER initial boundary condition, it didn't fully correct it, but it moved it up by about 2.5 hours. So looking at some chemical skill, there's no particular order. I'm starting with isoprene. So we had isoprene measurements from the Bertram group shown as the black dots. This divided into an early period of the campaign when isoprene was relatively low and a later period of the campaign when it was higher. And then let's focus on mean bias. So the base model was a half part per billion too low on average. If we double our biogenics, we're still low. And even when we put in those warm temperatures of the HER-NOAA model, we're still a little bit low. So the model doesn't have quite enough isoprene in it, but this needs to be taken with a grain of salt because isoprene has intense variation at the sort of 100-meter spatial level, depending on how many trees are right around your site. So it's smarter to look at longer-lived compounds like formaldehyde, and that's what I have here. So this is the Sheboygan formaldehyde. As Brad showed, doubling biogenics in his model added 0.65 parts per billion on average to formaldehyde at Sheboygan. And we haven't worked the numbers, but we get a similar increase from our base in red to the green, which is the doubling of biogenics. And performance is not too bad for formaldehyde. And then we can also achieve an increase in formaldehyde by increasing the anthropogenic hydrocarbons. So either one, they both get oxidized partially to formaldehyde, so this makes sense. Ozone. So here are some ozone traces, and we've been talking about this June 2nd event and how NAM CMAC, as Brad discussed, was too low. Well, WRF Chem, with a totally different mechanism and different MET, was also too low during this event. And just looking at mean statistics, once we switch to the HER-NOAA, we become unbiased on average with a mean bias of 0.6 ppb positive at the site. But this is, for all hours, and we're still missing the peak ozone levels that you can see here. The HER-NOAA is the green trace, and it's too low on this event here. All these are still too low. Interestingly, the biogenic I'll talk about on another slide. So Brad showed a large increase in Zion and over the whole southern part of Lake Michigan for increasing biogenics on June 2nd, and WRF Chem does not. So ozone, that was ozone at Zion. Here's ozone against scientific aviation. And I guess what I can point out is we're too low at the lowest layer. So black is observations reaching up to 85 parts per billion. The base model was more like 50. And the warming things up with the HER is the green, and that increased things a little bit, but didn't bring it up to the observation level. We also have ship measurements of ozone that kind of say the same story. The base is in red, the ship measurements. So this is now a moving target that's traveling all around Lake Michigan and sometimes sitting in port. Switching gears again to NOx. So let's start with our measurements in black at Zion. The base model run was in red. The mean bias was, we had a mean simulation of 6 parts per billion of NOx and a measurement of 2.8. So we were a little bit high. If we cut our NOx
50%.
in half from our base, then we become low biased in NOx. You don't want to just assume that it's all the errors in the emissions, right? Because this can also be transport and chemistry, or the spatial distribution of the emissions rather than their absolute amount over the airshed. NO2 comparisons between the model and scientific aviation kind of say the same story in that the base model at the lowest levels is a little bit high. So with a median of around 1 compared to scientific aviation's measurements of around 0.6. And then that's over the lake. Over the land, there was similar difference. I haven't studied in detail. We have started to do comparisons with Pandora and Geotasso and other NOx measurements that were like at Milwaukee and other sites. So there's more to come on this story. So we had improved ozone performance when we increased anthropogenic emissions, but we do measure some VOCs at Zion, and so what I'm showing now are observed levels of ethane for different days at the Zion site. The base model's in red, and a 5 times increase in domain-wide anthropogenic emissions is in green. So if you just look at ethane, it looks like the base emissions were too low and they need to be perturbed high. But if we look instead at benzene and toluene added together, you would have the opposite conclusion, that the base model was already too high and this data would not support increasing that specific hydrocarbon. I've alluded to these sensitivity runs, so I'll just take you to the upper right. So this is the increase in ozone from doubling biogenics, and we do not see that 30 parts per billion that Brad saw. We're seeing more like 3 to 5 parts per billion. However, when we increase anthropogenic hydrocarbons, we do see like a 20 to 30 part per billion increase over the southern part of the lake.
Charlie, is that averaged over the whole period?
I don't know.
I asked Miriam and Megan that last night, and I have not heard back.
I think it is, because if we average over the whole period, the 2X bio gets about a 2 part per billion enhancement. I was showing just on June 2nd.
Right. So, but you see, we don't get the 2 bio is the green trace.
Yeah. We don't get the same response on June 2nd, but we might get similar responses averaged over the whole domain time period.
I think it's averaged from 531 to 620.
Okay. So to summarize, I know these are a lot of. I am going to read these because I think they're important. The HER initialization and the NOAA land surface model do good things for our modeling system and bring the mean ozone to approximately unbiased levels. We're low on isoprene even after doubling emissions, with the caveat that that may not mean the emissions are too low. Formaldehyde is also slightly low. And it is sensitive to increasing hydrocarbon emissions. Ozone levels in our model are weakly sensitive to temperature. NOx is biased a little bit high in our base case simulation. And so far, conclusions made using the Zion data, the ship data, and scientific aviation are relatively consistent. Peak ozone in the southern portion of the lake in our modeling system is strongly VOC sensitive, and it's particularly sensitive in our modeling system to anthropogenic hydrocarbon, at least for that June 2nd event. I didn't show these, I didn't point out this, I did show it, but peak ozone in the southern portion of the lake in our modeling system is insensitive to NOx emissions. And we're seeing approximately the same formaldehyde sensitivity to biogenics that NAM-CMAC is, but we're not showing the same ozone sensitivity. So that's a big, interesting thing to look at going in the future. So this is really nicely complemented by the box modeling that Michael Vermeulen and company at Wisconsin have been leading. The reason that this makes sense is that we have measurements at Zion of hydrogen peroxide and nitric acid, which have been proposed and used sometimes as an indicator ratio, whereas if you have VOC limited conditions, then you terminate your radical pool through the OH reaction with NO2 to make nitric acid, and you don't have a lot of hydrocarbons around, so you don't make much hydrogen peroxide. So by looking at this ratio of nitric acid to hydrogen peroxide, you can see what your limiting species are. But it's complicated because we're measuring these plumes after hours and hours of processing in the atmosphere. And so Michael's box model explicitly represents all that processing, and you can see what at least the modeling system says happened along the way to Zion when you can measure sort of at the end of all the processing ratio of peroxide and nitric acid. So this is just showing for this June 2nd event the increase in ozone over the day and the decrease in NOx as you move from the source region to the receptor. And I apologize, I've had to abbreviate this so much, Michael, but I'm just showing highlights. So as the NOx decreases, so does the VOC reactivity from about 6 inverse seconds down to a minimum. And then Michael's model showing that as additional biogenics come into the parcel at the very end as it crosses back over land, slightly increasing the reactivity. And we want to point out that the measured reactivity of about 3 inverse seconds matches his base case model. And then net ozone production is shown here and peaks at around 10 parts per billion of ozone per hour in the model. And the colors here indicate the sensitivity of VOC or NOx, right? And values above 0.5 are VOC sensitive, NOx saturated, and the lowest value is way above 0.5, so at 0.8. So through it's initially starts at the highest number, 0.96, where it's highly VOC sensitive. Its VOC sensitivity decreases over time, but it remains VOC sensitive throughout the whole time. And if you take sort of the average ozone production of around 7 parts per billion per hour times about a 7-hour lifetime, you get this 50 ppb increase in ozone in this parcel as it advects from the source to the receptor region. And then because it's an efficient, fast model, you can run it over and over with different levels of NOx emissions and different levels of VOC emissions, building an ozone isopleph. And this is where Michael's modeling indicates that we are on the VOC sensitive side. So if you wanted to decrease, instead of getting a net ozone production of 50 parts per billion, if you wanted to get 40 parts per billion instead, you need to move from the green to the blue-green, right? And the most efficient way to do that is it's actually in this modeling system to increase NOx a little bit and decrease VOCs. In our modeling, we increased VOCs moving to the right here and saw significant more ozone production, and Brad showed the same thing. So I think it's we're starting to arrive at a consensus here where 3 independent modeling systems are all saying this June 2nd date is highly VOC sensitive. So now I think I really appreciate Tim and Michael letting me talk over all their work, and we should open it up to Michael.
Give me a second. Let me unmute you, Michael. Where are we here? Okay, Michael.
And that's the end of so we can also open it up to general questions as well.
Okay. Well, thanks, Charlie. That's a lot of information. Great presentation. So as I mentioned, for those of you on the line, Michael, I unmuted you if you have anything to say, but for the rest of you, if you'd like to ask a question, raise your hand using the raise hand column in the client, or you could type in a question into the questions box.
I can just take any questions since it doesn't seem like we have too much time, and that was gone through pretty quickly, so I could clarify anything.
All right, thanks, Michael. Yeah.
I have a question. It's going back to, I think, 2 presentations earlier where we're looking at the concentrations of isoprene versus some of the products, and you had a time series chart showing isoprene with those products. This is Mark Jansen from LADCO, by the way. I don't know if you could back up to that slide. It had the isoprene in black on the bottom.
Slide 5, mine.
Yeah. I think it was that one. Yeah.
All right.
So as an inventory person, I sort of see this and say, wait, the inventory is generating plenty of isoprene, but something's happening in the production side in the model of the sulfate. Is that right, or is there something else there that should be influencing that, or do we think that some spike in isoprene or something else is the cause of that we need even a greater spike in isoprene during that day, but we'd assume that all the other days would spike as well?
Those are observations, though. Those aren't models.
Right. Yeah. So if we can get a lot of isoprene and still show none of that product, there's something going on in the chemistry during B to create those high concentrations. It isn't like direct emissions are necessarily the driver there, are they?
Well, I mean, the lifetimes of these compounds might be quite different. So I don't know the lifetime of methyl tetrol sulfate, but I am guessing that it's days, and isoprene's lifetime is hours. And so the methyl tetrol could be coming from anywhere in the domain. And so that's an interesting question to look at, is can we tell whether that might be long distance transport of some of that SOA, and then the isoprene is more of a local story because it is so reactive. And so by looking at more reaction products, we might be able to tease that apart. The other thing that immediately I thought of is just the sulfur availability. Maybe time B has a lot of sulfur dioxide available, and maybe time C is coming from a different location with less SO2 emissions. So these are answerable. But unfortunately, none of this chemistry is in our model. It might be in Michael's with those 8,000 reactions.
Betsy, you're unmuted.
Yeah, I was just going to add there are two additional observations that I think are starting to help us understand what's different between B and C. And it is indeed true that there's more sulfate in the PM 2.5 on a relative basis during period B compared to C. And the formation of methyl tetrol sulfates in these isoprene products is highly sensitive to sulfate as well as aerosol acidity. And that brings me to the second observation, and that is there was a change in relative humidity between B and C with, I believe, lower relative humidity in B, which kind of led us to this hypothesis that with a higher sulfate and lower liquid water content, we perhaps have more acidic aerosol during period B compared to C, although the thermodynamic modeling that Dagan's been working on has not been conclusive yet.
And I think that's sort of my concern is that if we just simply double isoprene or double biogenics, we don't chase those other things, because I know the lever to hit to double emissions is an easy lever to hit, and those other levers are very hard to understand. But I think we just caution against flipping the inventory lever because it's an easy lever to flip. Not to say that I can't be critical of inventories. I spend my life being critical of inventories, but I think we want to modify them when we really think there's something in the chemistry that justify a modification.
And many of the times when we move the emissions, it's to determine sensitivity of the system to those, not necessarily to say that we're moving towards a more accurate. I mean, if you look at the deliverable that we promised NSF, was to say we want to quantify the sensitivity of this system to changes in NOx and VOCs, and then to split out that VOC sensitivity into biogenic and anthropogenic VOCs.
But that comes back to inventory people as, your VOCs are off by 5 times. Just to be cautious of it.
I understand.
Are there any other questions from the audience? Well, if not, I will say that we've been recording this webinar, and we'll post the webinar recording on the LADCO LMOS website at some point next week. I really appreciate the time and effort put together by the entire research team, and particularly to Brad and Charlie for putting these slides together and making this great presentation to us today. Before we sign off, let me ask Brad and Charlie if you could give us a quick synopsis or rundown of where you see yourselves going with this work over the next, say, 6 months. Brad, what are your plans?
So we're continuing to do some other MET sensitivities. Those are in particular looking at the influence of soil moisture and better predictions of that. We're waiting on partners at NASA Sport to deliver that. In the meantime, we are moving forward and trying to look at the impact of these different MET configurations on the CMAQ chemical predictions. At this point, we're only able to do that with the 12-kilometer simulations, and as we saw, the differences between our different configurations are fairly small for that. So we're, as soon as we can get higher resolution emissions for this time period, or even 2016, then we can proceed with looking at impacts in the chemistry at higher resolution, along the same lines of what's already been done with WRF Chem.
Great, thank you. What are your plans, Charlie?
We're trying to kind of button up some of the stories into formal publications, and the ones that are at the top of my head right now are documentation of the observed lake breeze during the study is one that we've started to work on, and then kind of preliminary documentation of how the models did at representing that lake breeze, and then I've been showing a lot of, we've compared to 1 or 2 or 3 time series or observations, and we want to standardize that to the full comparison to all available observations and standardize our statistics so that, because in the end, I think people do want to see those kind of apples to apples comparisons between the different model configurations and chemical mechanisms and how they represented different time periods and spatial locations.
Okay. And is there a central location where we're maybe listing what the publications are for this coming out of this research?
I think the NASA repository is the correct place to do that, and then to mirror it on the LADCO website would be my suggestion. We have not discussed this.
Okay.
We want to create the problem of having publications to list first.
Got it.
Yeah, I'll follow up there. We'll be taking the interim or the synthesis report, and that'll become the basis for probably a BAMS article that would be an overview of the field campaign. And yeah, I would agree that having NASA as the repository for papers, draft papers, and things would be the right place right now.
Okay. Well, thanks again to you all for these great presentations and taking the time today to report out on your work. Great work, and I look forward to what comes next. And I hope everyone has a great weekend.
Thank you.
Thanks, everyone.
That's easy, especially.